is the absolute structure of an atom. So, have you ever imagined how small a single atom could be? It is beyond your imagination. Let us see. So now I think you are clear at how small a single atom could be. So let's start.
You might have observed that after rubbing a balloon against air, it sticks to the wall. Can you guess why this happens? It happens due to the development of the opposite charges on the balloon and the wall. These opposite charges attract each other. The charges on these two in turn develop due to the charged particles present in them. In fact, such charged particles are present in every matter. Now let us see where actually these charged particles are present inside matter and what are these. We know that matter is made up of atoms, so it is the atom which has these charged particles. When positively charged, these are known as protons. When negatively charged, these are known as electrons. Now that we know that what these are, it is also important for us to know by whom they were discovered and how. The credit for the discovery of electron goes to Sir J.J. Thomson. An experiment that helped him discover this was the cathode ray tube experiment. The setup of the experiment consisted of a glass tube containing a gas, two electrodes at its two ends connected to a battery. The gas inside the tube had a very low pressure, which was maintained with the help of vacuum pump. On passing the electric discharge, the rays called cathode were produced, which were attracted towards the positively charged plate. As these were attracted towards the positively charged plates, these were supposed to be made up of negatively charged particles, which were named by Sir J.J. Thomson as electrons. So this is how the negatively charged particles were discovered. Since atoms are neutral, it was concluded that some positively charged particles must also be present in the atoms. These positively charged particles were later discovered by Goldstein in 1886 as protons. The experiment set up for the discovery of proton was similar to the cathode ray tube experiment we saw before. The only difference was that Goldstein took perforated cathode in the middle and a fluorescent screen at the other end. On passing the electric discharge, the rays were observed, which traveled in the direction just opposite to the cathode rays. These were named as canal rays and they passed from canal like holes. As the direction was just opposite, it was concluded that these must be made up of some positively charged particles. These positively charged particles were nothing but the protons. So now we know that all atoms have two types of charged particles, that are electrons, the negatively charged particles, and protons, the positively charged particles.
After the discovery of electrons and protons in an atom, the next challenge in front of scientists was to know about their agreement inside the atom. Sir J.J. Thomson was the first scientist to provide the structure of an atom from inside. Thomson proposed that an atom consists of a positively charged sphere that is made up of protons. All electrons of the atom are embedded in this sphere. Moreover, according to him, the negatively and positively charged particles, or in the other words, the number of electrons and protons, were equal. This model was also known as the watermelon or a plum pudding model because of its similarity with these two seeds of watermelon can be equated to the electrons or the negatively charged particles, and the red mass can be equated to the protons or the positively charged sphere. Similarly, in a plum pudding, the raisins can be considered as the electrons and the remaining portion can be considered as a positively charged sphere.
A number of scientists worked on the structure of an atom. One of the first scientists was Sir J.J. Thomson, but his model could not explain the results of several experiments. One of those experiments which could not justify the Thomson model was done by Rutherford. Rutherford experiment got popular by the name of alpha particle scattering experiment. To understand about his experiment, let us first see what alpha particles are. Alpha particles are emitted by radioactive substances. These are helium ions, double positive charge. Now let us look into the detail of the alpha particles scattering experiment. The setup of the experiment consisted of a big lead box with a hole on one of its walls, a slit, a thin gold foil, and a rotating detector at the end. Inside the lead box, a radioactive substance rich in alpha particles was kept. Now let us see the experiment. Alpha particles emitted from the radioactive source passed through the hole and entered into the slit to get streamlined. Within streams of the particles then bombarded the gold foil and got scattered in different directions. Their scattering pattern was shown by the detector. It was expected from the Thomson model that it should show a large number of deflections, but something else was observed. Actually, the detector showed that most of the alpha particles passed through the gold foil as such without showing it deflections. Only a few of them showed deflections in different directions. A very few of them, essentially 1 in 12,000, rebounded back. Such observation led to significant conclusion. Let us see what these were. As most of the particles passed undeflected, Rutherford concluded that most of the space inside a gold atom was empty. A few of particles were deflected from their path by small angles, indicating that there must be a positively charged center, which was repelling alpha particles. As these particles were few in number, this led to the conclusion that a positively charged center occupies a tiny space. The few particles that are rebounded back indicate that all the positive charge of the atom was concentrated in a very small volume in the center. Rutherford named this positive center of the atom as the nucleus. Looking at the proportion of the particles undeflected, deflected and rebounded, and based upon some calculations, Rutherford concluded that most of the mass of an atom is concentrated in its nucleus. Based on all these conclusions, Rutherford suggested an atomic model which was known as the nuclear model of atom. According to Rutherford's nuclear model, there is a positively charged center in an atom called nucleus, and and all the mass of an atom is due to this nucleus. It also suggested that electrons of the atom revolve around its nucleus. This model was also known as planetary model, as the nucleus of the atom can be compared to the miniature sun, and electrons revolving around the nucleus can be compared to the planets revolving around the sun. But this model did not get much acceptance, as it is said that electrons keeps revolving around the nucleus. However, later it was found that any charged body while moving in a circular motion undergoes acceleration. On undergoing acceleration, it should use some energy, so the energy of the electrons should keep decreasing. As a result, the path in which the electron is moving should keep becoming smaller, and thus finally it should fall into the nucleus, and hence the atom should collapse. So the nuclear model could not explain the stability of the atom, and this was its major drawback.
Prior to Bohr, there were a number of scientists who were working on the structure of atom. Rutherford was one of them, and his model was the closest model to Bohr model of an atom. In fact, Niels Bohr had helped to overcome the problem in the Rutherford model of an atom. On the Rutherford model of an atom had a major drawback that it could not explain the stability. It shows that electron in an atom revolve around a positively charged center called nucleus. However, later on it was found that any particle in a circular motion would undergo acceleration and thus would lose energy. So the electron would take a spiral path and would finally fall into the nucleus, and the atom would collapse. But this does not take place in reality. Bohr said that electrons do revolve around the nucleus, but their energy remains fixed. He explained that the energy of electrons remains fixed because they are restricted to some fixed orbits. Each of these orbits is at a fixed distance from the nucleus and is associated with a fixed amount of energy. These orbits with fixed energy are known as discrete orbits or energy levels. These energy levels are represented by the letters K, L, M, N or the number 1, 2, 3, 4. Starting from the center, so the final model of Niels Bohr was similar to the Rutherford model of an atom, which said that an atom consists of a positively charged center around which the electrons revolve. The only difference was that in the Bohr model, electrons revolve around the nucleus in fixed orbit with fixed energy. Niels Bohr got a Nobel Prize for his work in structure of atom in 1922.
After the discovery of electrons and protons, scientists attempted to calculate the atomic masses of different elements. Scientists thought that as mass of electrons is negligible, mass of an atom should be equal to the total mass of protons present in it. If that were to be true, the mass of a carbon atom should be equal to the mass of 6 protons present in it. But that was not true. Experimental studies proved otherwise. The mass of a proton was found to be much less than the actual mass of an atom. It was thus concluded that the excess mass was due to some other particles that had considerable mass. Later in 1932, James Chadwick discovered neutrons through a series of scattering experiments conducted to prove the interior of atoms. He was awarded the Nobel Prize for Physics in 1935 in honor of this important discovery. Let us now understand this experiment that enabled the discovery of neutrons. In this experiment, alpha particles were projected towards a beryllium foil. As a result, the beryllium foil was found to emit some mysterious particles that had neutral charge. These rays were allowed to pass through a slab of paraffin wax, which resulted in the release of charged atoms due to collision. These charged atoms were then made to enter a chamber filled with gas. The charged particles ionized the gas, which led to the drift of ions towards the electrode, constituting a current. By measuring the current, the mass of the ejected atom was estimated, which led to the conclusion that the mysterious rays consisted of particles whose mass was almost same as of that of the proton. Chadwick identified these uncharged particles as neutrons. The mass of the neutron was found to be 1.678 into 10 raised to the power minus 27 kg or 1.00866 AMU. After the discovery of all subatomic particles, it was concluded that an atom is made of electrons, protons and neutrons.
Knowledge to know. Sir J.J. Thomson. J.J. Thomson, a British physicist, was born in Cheetham Hill, a suburb of Manchester, on 18 December 1856. He was awarded the Nobel Prize in Physics in 1906 for his work on the discovery of electrons. He directed the Cavendish Laboratory at Cambridge for 35 years, and 7 of his research assistants subsequently won Nobel Prizes. E. Rutherford. E. Rutherford was born at Spring Grove on 30 August 1871. He was known as the father of nuclear physics. He is famous for his work on the radioactive and the discovery of the nucleus of an atom with the gold foil experiment. He got the Nobel Prize in Chemistry in 1990. Niels Bohr. Niels Bohr was born in Copenhagen on 7th October 1885. He was appointed as the professor of physics at Copenhagen University in 1916. He got the Nobel Prize for his work of the structure of atom in 1922. Among Professor Bohr's numerous writings, 3 appearing as books are The Theory of Spectra and Atomic Constitution, Atomic Theory and The Description of Nature, Schematic Atomic Structure of the First 18 Elements, Hydrogen, Helium, Lithium, Beryllium, Boron, Carbon, Nitrogen, Oxygen, Fluorine, Neon, Sodium, Magnesium, Aluminium, Silicon, Phosphorus, Sulfur, Chlorine, Argon.
Let's recap. So, J.J. Thomson was the first scientist to provide the model of an atom. His model was similar to watermelon, a plum pudding. According to his model of an atom consists of positively charged sphere made up of protons and electrons are embedded in it. He also proposed that an atom consisted of equal number of electrons and protons. His model did not justify the results of some experiments later.
Rutherford gave a nuclear model of an atom which was based on this alpha particle scattering experiment. According to the Rutherford's model of an atom, all the positive charge in mass of an atom is concentrated at the center. The center of the atom is called the nucleus. The size of the nucleus is very small as compared to the size of an atom. The electrons of the atom revolve around the nucleus. The major drawback of this model was that it could not explain the stability of the atom.
Bohr model of an atom suggested that an atom consists of a positively charged nucleus and electrons revolve around it in a special type of orbit called discrete orbits or energy levels. The energy of these discrete orbits remains fixed. These energy levels are represented by 1, 2, 3, 4 or KLMN. Starting from the center, Bohr got a Nobel Prize for his work in 1920.
An atom consisted of electrons, protons and neutrons. Neutrons were discovered by James Chadwick in 1932 by bombarding beryllium nucleus with alpha particles. Neutrons were neutrally charged particles whose mass is equal to 1.678 into 10 raised to the power of minus 27 kg or 1.00866 AMU.